Okay, can we just quickly have a look at this one here? So this is slightly different. I'll change it to what's on the sheet there. Okay. So we've been given z is equal to root 5 e to the 3 pi I. Now, first of all, what form is this complex number written in? So Cartesian, Euler, or modulus or argument form? It's Euler form, right? Because you've got this e in here, okay? Sorry? No, I know. Exactly. Yeah, this is in Euler form, okay? But you can still extract the modulus and argument from it really easily, just like you can with polar form, okay? So what would the modulus be? Yep, root 5. And what would the argument be? 3 pi. Fantastic. In fact, if you wanted to sketch this, on the complex plane, what would this look like? If I wanted to sketch this complex number on the complex plane, what would this look like? I mean, think about what 3 pi is. What does that actually mean? It means you've gone round once, twice, 3 times. You're on the real axis. So actually, this is a real number. This is a real number. It's just negative root 5. Are you happy? So actually, it would be out here at negative root 5. Okay, out there at negative root 5. Right. But what I want to do, I'll change the question slightly to what's on the sheet. Let's suppose I want to find the 4th root of z. I want to find the 4th root of z. So first of all, how many solutions am I expecting here? How many? I'm selecting 4 solutions. I'm expecting 4 roots. Okay. So how do I go about doing this? What's the first thing that I would do?
Find the base root.
Exactly. First things first, I will find the base root, and then everything else will just be equally spaced. All the other roots will just be equally spaced off of that with the same modulus as the base root. So would you be happy that 4th root of z would be the same as taking z and raising it to the power of 1/4? To find the base root, how do I do that?
Put the modulus and argument in the Cartesian form.
Would you?
No. Look at De Moivre's theorem.
De Moivre's theorem, perfect. So I'd use De Moivre's theorem to find the base root. So I'm basically saying I'm taking this complex number, and if I want to raise it to the power of 1/4, then I should raise the modulus to the power of 1/4. So I take root 5 and raise that to a power of 1/4. And I should also multiply the argument by 1/4. Okay? So e to the 1/4 lots of 3 pi, lots of I. You notice De Moivre's theorem will also work in Euler form as well. Okay? This still extends to Euler form. Yeah? Just like with modulus argument form, it will extend to Euler form because it's the same idea. Okay, you're doing that stretch, in this case shrink inwards, and you're also rotating the complex plane by that many times, 3 pi, and you're doing only 1/4 of that term. Is that okay? Okay, good. So that's the base root. So actually, let's plot this on my sketch. So, right, root 5 to the power of 1/4. Would you be happy that that would be equal to the 8th root of 5? Yeah? And would you be happy this would be 3 pi by 4? Lots of I. Okay? So 3 pi by 4i, 3/4 of pi, would be about here. Are you happy? Yeah? You about there? So here it is. And also it's going to be a lot smaller than my original modulus. So that's my first root. That's my base root. Let's call that z1. Okay? Now, where are the other 4 roots going to lie? So what's the spacing between the 4 roots? What's the spacing between these 4 roots? How do I calculate this? Absolutely. I take the entire rotation, 2 pi, and divide it by the number of spaces between my roots, which in this case is 4. So actually, they will lie at 90 degrees or pi by 2 radians apart. Okay? So there's one here. There'll be another one over here. There'll be another one over here. And there'll be another one up here. Okay, so those are my 4 roots there. Okay, so effectively, once I've got my base root, the other 4 roots will just be another pi by 2 radians further on. So the distance between that and that is pi by 2. Distance between that and that is pi by 2. Distance between that and that is pi by 2, and the distance between that and that is also pi by 2. Okay, so I just add pi by 2 every single time. So if that's Z1, okay, then Z2 will be this, so the 8th root of 5, it's still the same modulus. Then I take 3 pi by 4, and I add on pi by 2. Okay? And then Z3 will be the same kind of idea, so I take the 5th root of pi, e to the power of, right, okay, let's tidy this up slightly just quickly. So it'll still be the 8th root of 5. It'll be e to the power of 7 pi by 4, yeah? I. Okay, so in which case this one will just be that plus another pi by 2, yeah? Oh yes, 5, sorry. Yep, it's Friday morning. There you go, 5. So literally what I've done is I've found Z2, so to find Z3 I just need to turn another pi by 2 further on. So I just need to increase this argument by another pi by 2. So in which case this becomes 8th root of 5 e to the power of 7 pi by 4. That one's a 7 pi by 4. That's all right. And then Z4, nice and easy, will just be the 8th root of 5, same modulus. You take that argument, so 7 pi by 4, and you add on another pi by 2. In which case that's going to be 8th root of 5 e to the power of 9 pi by 4. So what's literally happened here, so no, it won't be the same as the base root. This is the base root over here, okay? It won't be the same as the base root, because if you notice, 9 pi by 4 is the same as 2 and 1 pi by 4. So what's literally happened here is you've done one full rotation, that's your 2 pi bit, plus an extra pi by 4 on top. So the other way which you could write this, if you wish, is to say this is the same as the 8th root of 5 e to the pi by 4i. That's fine as well. Okay. All that 2 pi means that you've just done one full rotation round, then you've got an extra pi by 4 on top. So it's fine to write like that as well. Because you remember your angle is measured anti-clockwise from the positive real axis. Okay. So my 4 roots are this one, this one, this one, and this one over here.
How you get the 8 root 5? I don't understand.
This one here is just coming from this, okay? So let's think about this, good question. It's just laws of indices, okay? So the square root of 5 could be written as 5 to the power of 1/2, okay?
And you plus,
And I'm raising all of that to the power of 1/4. So by laws of indices, that should be equal to 5, exactly, 1/2 times 1/4. So I multiply the powers together. Hence I get 5 to the power of 1/8. And if I put that back into surd form, I would write that as the 8th root of 5.